Good morning, everyone. Welcome to this image classification with Hugging Face course. My name is Priyanka Asnani, and I'm currently working as Senior Machine Learning Engineer at Fidelity Investments. So, in this project, we'll explore the capabilities of vision transformers uh, for various image understanding tasks like simple image classification, zero shot image classification, and zero shot object detection task. So, by the end of the project, we'll understand the potential of vision transformer models in handling diverse image related challenges. So, the first application that we are going to cover is simple image classification. So, this application involves training a vision transformer model to classify images into predefined categories. So, it serves as a foundational example of using VIT for image understanding. The second application that we are going to cover is zero shot image classification. So here the project explores the capability of VIT model to classify images into categories that it has never seen during training. So this task demonstrates the model's capability to generalize new classes, which is a very crucial skill in real world scenarios. The third application that we are going to look at is zero shot object detection. So this task goes beyond classification and involves identifying objects within images even if the model has never seen or encountered those objects during training. It showcases the VIT's model potential for object detection in novel context. So the intended audience for this project target individuals with an intermediate to advanced level of knowledge of machine learning and computer vision. The project assumes that a basic understanding of deep learning concepts and coding proficiency in Python. So, the first task that we are going to cover is setup, where we are going to install and import various libraries that you will need to run this notebook. So, for this image classification task, we need transformers, which is our first package. So, we are going to install it here. So we already have transformers involved, so we are just going to import transformers library. So from transformers, okay, so we already have transformers, so we can just go ahead and install the vision transformer feature extraction and image classification models. So the feature extractor or VIT feature extractor helps us extract features from the images. So we can just copy paste this package and then we can load this model for the image classification task. And the other package that we need is the image package, which we'll use to download the images from the web. So we can just do from PIL import image. The next package that we are going to import is request library. Then we import torch package. And in the end, we import matplotlib library, which will help us do some plots. Import matplotlib dot typeplot as plt. So now we'll run the cell. Yeah, looks like we have all these packages imported now. So next task we are going to cover is we are going to load the vision transformer models, right? So in this task we initialize both the feature extractor and the pre-trained vision transformer model for image classification task. So in this case, we are going to use VIT base PAT 16224 model, which is a very popular choice for various computer vision tasks. So What this name signifies that this model has a path size of 16 by 16 pixels, and it's trained on a model. It's trained on a model with 224 by 224 pixel images. So just in computer vision, patch size refers to the dimension or size of a rectangular region or patch that is extracted from an image. So we can say that the features that are being extracted from the image are being referred here as the patch size. So this patch can typically contains a subset of the pixels from the original image and is used for various computer vision tasks. So instead of using the entire image pixels, we just extract a subset of those image pixels from the image and then use those image pixels for various computer vision tasks like feature extraction, object detection, image classification, and image processing. So we will first try to load the feature extractor and the model here. So we'll write some code. So we'll first load the feature extractor for the vision transformer. Feature extractor, we'll create a variable and then we will use the model, use the feature extractor that we previously imported, and then we use the from pre-trained function, and then we just load our feature extractor. The model was developed by Google, so we are downloading from Google. We downloaded it, we imported it, and this is how we give the path to the model. So feature extractor is the variable where the model will be, where the extractor will be loaded. VIT feature extractor from pre-trained, and the name of the feature extractor. Because we have multiple feature extractors, so we need to specify which feature extractor are we going to load here. The next is we are going to load the pre-trained weights from the vision transformer. So we are going to use a variable called model, and then we are going to use our model VIT for image classification. We again use from pre-trained function, and yeah, and then just give the same path, same model name for this model, and now we try to run it. So we see that our feature extractor and our image classification model has now been loaded. Sorry. Okay. So the next task that we are going to cover is we are going to generate features from an image. So we will take an example image. Here in this case, we are going to take an image of a laptop and then just try to extract features from that image using our feature extractor from the vision transformer model. So as we saw in the previous task that we loaded the feature extractor and the pre-trained model vision transformer, in this task we are going to extract features from an image using pre-trained visual transformer model. Extracting meaningful features from an image is a very crucial step in various computer vision tasks. These features serve as a representation of image that can be used for various tasks such as image classification, object detection, image captioning, and more. So the first step is to actually load the image from matplotlib library. So we'll create a variable called image, and then we'll use plot function, plot.imread function, to read the image for further processing. Okay, so one thing I would like to mention that this image was downloaded from the web, and then we loaded this laptop image here, and you should be able to find this image under Files tab. And then yeah, we load this image, and then we are going to just display this image, and we are going to run this cell. So we see this is an array of pixels that is being printed out. But we can actually display the image using plot.imageShow function. If we use imageShow function of matplotlib library, we'll be able to actually display this image of the laptop. And in the next step, we are going to extract the features from this image. So we'll create a variable called inputs. We'll use feature extractor function. And then we pass in our image. So here we use a feature extractor function. From the vision transformer model, we pass in our image, and also we pass in an argument saying that return tensor is equal to PT, which ensures that which specifies that the features that are being extracted will be returned as PyTorch tensors. So now we are going to run this cell. Okay, so we were able to run this cell successfully, and all the features that were being extracted are stored in this inputs variable that we are going to use it for our image classification task. So the next task that we are going to cover is image classification. So in the previous task, we learned about the functions that can help us extract features from an image. In this task, we are going to make the predictions for the image using the pre-trained vision transformer model. So the first step, we are going to create a variable that holds the pixel values for this image. So let's create a variable called pixel values. And then we have the inputs variable, which has all the features that are being extracted from for the image of for the laptop image. So we are just going to just load all the features here. Pixel values. And now we are going to make the predictions for this. We are going to make the predictions for this laptop image using our vision transformer model. So we have outputs equal to model that we loaded in the previous step, and pass in our pixel values variable, which contains all the features from our laptop image. So we are going to run this cell. Okay, the cell ran successfully. So the next step is we are going to extract these scores for different classes. So these scores are nothing but the probabilities of different classes that this model is being trained on. So we are just going to extract the different probability scores. So we are going to create a variable called logits equal to outputs.logits. And then we are going to print out the shape of this logits variable. So if we run this cell, okay, so if we run this cell, we get 1 by 1000 tensor, which means that this model is being trained on 1000 classes. So now we want to predict the class for this, for our laptop image. So we are going to find the index of the predicted class with the highest probability. So we are going to create predicted class IDX. So after we ran this model on our laptop image, it generated some probability score for each of the classes that the model was being trained on. So now we are just getting the class which has the highest probability. Logits dot argmax. We'll use argmax function, which actually gives you the max probability. -1. And now in the next step, we are just going to display the index of the class which has the highest probability. So we are just going to print out this variable name, and let's run this cell. Okay, so I got an error that logits is not defined. Okay, I think it was a typo. So I think now it should work. Yeah. So we see that our predicted class is 680. Predicted class has an index of 681. And now we are going to get the class name corresponding to this index. So we are going to create a variable, predicted class, model.config. Dot id to label. So here we are using this function to convert our id, which is 681 here for our laptop image, and then we are going to get the corresponding label for this index. And here we are just going to display the predicted class. So it says it predicted, it got the name corresponding to the index x81, and it says notebook computer. So which means that the model predicted this image correctly and was able to classify this image correctly. So it's a laptop notebook computer, and model was able to classify this image correctly. The next application that we are going to look at is zero shot image classification. So in the previous task, we learned about simple image classification using vision transformers. In this task, we will learn to load pre-trained models for zero shot image classification task. So what is zero shot image classification? The zero shot image classification, it allows a model to classify images into categories which the model has not seen during training. So this is a very crucial application in real world where new categories may constantly emerge, and it's not feasible to retrain the model every time when we see a new category or new categories are being introduced. In this task, we are going to use OpenAI clip with large patch 14 model because they excel at zero shot classification task. With a simple textual description or prompt, you can use these models to classify images into categories which they have not seen during training. This is very valuable when you have very limited label data for image classification task. So the first step we are going to do is we are going to load the necessary classes from the transformers library to work with a pre-trained model for a zero-shot image classification task. So let's load the pre-trained model. So we are going to load these models from transformers. So from transformers, import auto processor and auto model for zero shot classification. The model for zero shot image classification. So we load the model for the classification, and we also load the processor, which are responsible for tokenizing and processing the inputs to make them compatible with the model. So in this case, we are using auto processor to handle the text inputs and prepare these inputs for the model classification. Next, we are going to specify the checkpoint name. So our checkpoint is this model. So we are specifying which model we would like to use from this library. So next, we initialize the pre-trained model. So we are going to create a variable called model, and in this model variable, we are going to initialize our pre-trained model that is being used for zero-shot image classification task. So we take this model and use dot pre-trained function and pass in our checkpoint name. We then initialize the processor that's associated with this pre-trained model. So we are going to use the variable processor, and we are going to copy paste the name of the auto processor. We are going to use the same pre-trained function and pass in our checkpoint. So let's run the cell. So it's still running. It will take about 10-15 seconds to run the cell. Okay, so now we have initialized our processor, we have initialized our model. So now we are ready to extract the features from our image. So now in the next task, we are going to prepare the inputs. So in the previous task, we learned to load the pre-trained model for the zero shot image classification task. In this task, we learned to prepare the inputs for zero shot image classification task using the processor that we initialized earlier. So let's look at the input. So here we are using this image. It's the image of a car. So we are first going to just open the image from this URL. So we are going to create a variable called image, and we are going to use the image library to open this image. Since this is a URL from which we want to open the image, we are you going to use the request package request.get URL dot stream equal to true. And since we are interested in seeing the raw image, we'll do dot raw. And then now we are just going to display this image. If we see, this is the image of a car. And now we are going to run our modeling, run our inference on this image. So let's first specify the candidate labels for classification. Since I mentioned earlier that this is a zero shot image classification task, so the model is not being trained on, this is a task where you get your model to learn labels which it has not seen during training. So first, we for this task we will have to provide some candidate labels for this classification task. So we'll provide a list of candidate labels. So let's create that list. So candidate labels equal to, so we assume that this image could be of a tree, car, bike, and cat. So we will pass all these candidate labels to our model. And then we prepare inputs for the zero shot image classification model. So we will extract features just like we did for our image classification task earlier. So we will create a variable called inputs. We will use the processor function, and then we will pass in our image. We will pass in our list of candidate labels, and we will also pass in return tensors to make sure that our tensors are returned as PyTorch tensors. And then we say padding equal to true. So padding ensures that we have consistent length during training, consistent length for the inputs during training. So let's run the cells. I missed an S here. Okay. So we are able to run the cell successfully. So the next task that we are going to look at is we are going to actually look at the predictions task. So how do we generate predictions for zero shot image classification task? So in the previous task, we learned about how to prepare the inputs. We looked at how to load the image, extract features from that image. In this task, we will learn to generate predictions for this image that we provided to the model. So the first step is that we use a torch-nograd function to perform the inference on the model. So the first step is to import PyTorch. And then we pass in the inputs to the model. So we use with forge.nograd function outputs equal to model, and that's where we'll provide our inputs. And then we extract the probabilities and calculate the probabilities. So we are going to use the logits variable. Output.logits per image. What this function is doing, that it helps it's helping us extract the raw scores from an image, for an image from the model output, and then we convert all these probability scores to a list. Logits.softmax. So since we have multiple classes here, so we are using softmax function, which allows you to give probability scores for all the classes that you have passed in your candidate list. So for us, we have passed in 4 labels: tree, car, bike, and cats. So it's going to give us the probability for each class. So that's why we are using softmax function here. .numpy, and then we are going to convert these probability scores to a list. So we are going to use scores equal to probs dot list, and then we create the list of results. So then we create list of results. So we create a list called result, which is a dictionary of score. Yeah, so this dictionary will contain the labels that we passed in as the candidate labels to this model, and also the score, the probability score corresponding to each label. So score, then score, then we have label, which is the candidate label that we passed in as a list. This is the first. And then we are going to iterate over this dictionary for score, candidate label, probabilities, and candidate labels. So we are using lambda function in Python to sort this list in the descending order. So it's in the descending order of their scores. So the label which has the highest score will be ranked at the top. So key equal to lambda x equal to minus x 0. And then here we just display the resultant list, which is nothing but ranked in the order of the probability scores. So let's run this cell. Okay, so we got an error that the dimension is out of range. Okay, so I think it was -1 and okay, let me verify if I wrote this code correctly. Okay, so I didn't use toList function. Now it looks okay. Okay, so the now here we see the dictionary with the scores and the labels. So for each label, we have the corresponding score. I think it should be candidate label. Okay, so I did some mistakes in my code. Okay, so here we see a list of dictionary with scores and the labels. So we have a label that we passed in as the candidate label to our model, and then for each label we have a corresponding score associated with it. So if and these scores, these lists are ranked in the order of the probability score. So if we see that the model has given highest confidence score to the label car, which is correct because the image that we initially passed into the model was for a car and it has predicted a correct. It has given the highest confidence score to car. So which means that model is able to make the right predictions for even for the labels that it has not seen during training. So what it needs just the candidate labels and it would still give that the label a very high score. In this application, this is the last application for this project. In this application, we will learn about zero-shot object detection. So in the previous task, we learned about zero-shot image classification using pre-trained model. In this task, we learn about pre-trained models that could help us detect objects in an image. So in many practical situations, there are object categories in an image that are very rare or seldom encountered in the training data. So zero-shot object detection helps us recognize and locate such infrequent objects effectively in an image. So the first thing we are going to do that we are going to load the processor and the model used for object detection, and just like we did in our previous task. So we are going to load our processor and the model from that transformers library. So from transformers, import auto processor, comma, auto model for zero shot object detection. So we are going to load these two models here. So auto processor, just like any other task that we covered earlier, it's going to help us the extract features from the image, and the object detection, zero shot object detection model will help us classify objects in an image, the objects that the model has not seen during training. So now we are going to specify the checkpoint name. So for this task, we are loading Google's Alwet base patch 32 checkpoint, which is associated with Object World Learning Vision Transformer model with a base architecture and a patch size of 32 by 32. As I said, the patch size is nothing but the features that the model extracts from the image. So it extracts the subset of the image, which is of the size 32 by 32. So we use this model because it has a smaller path size, which means that it is suitable for detecting smaller objects and fine grain details within the larger images. Also, models that work with smaller patches may have been pre-trained on a larger data set, which means we can always fine tune such models on your specific object detection task with relatively small amounts of annotated data. So we first load the processor that are responsible for preparing the inputs, tokenizing and pre-processing the inputs to make them compatible with the model. And then we load the auto model for zero-shot object detection model that will help us detect images, that will help us detect objects in an image. So let's specify the checkpoint. And then we are going to initialize the pre-trained model. So we have model, use this model, and then we use from pre-trained function, just like we did it in the previous task, from pre-trained, and then we pass the checkpoint here. We use the same, we then initialize the processor. We use from pre-trained function, and then we pass the checkpoint. Let's run this cell. Okay, so it took about 10 to 11 seconds to run this cell. So this cell ran successfully. So let's come to the next task. So here, just like previous task, we are first going to prepare the inputs for the model. So in the previous task, we learned to load the zero-shot image classification model. Now we will learn to prepare the inputs for this task using an image and list of textual queries. We will use, so let's first load the image. So we are using this URL to load the image. So we are going to open this image. So we are going to use the request library image.Open to call this URL. So request.get URL dot stream equal to true dot raw, and then we are just going to display this image. If we see, we have several objects here. We have hat, phone, book, sunglasses, orange. So we'll see in further tasks that our model is able to classify these objects and it is able to detect these objects in this image. So let's provide a list of textual queries describing these objects. So we are going to create a list named as text queries equal to, and then we'll pass in all the labels, all the objects that we feel, all the objects that are there in the image. So we see a hat, we see a book, we see sunglasses, and then we see a camera. So now we will prepare the inputs for this task. So just like previous task, we'll use the processor function. And then we are going to pass the first parameter will be the text queries. So we are going to pass in the text queries list. Then we are going to pass the image. So this is stored, our image is stored in the IM variable. So we are going to pass that. And then finally, we are just going to do return tensors equal to PyTorch, which means that this function should only return PyTorch tensors. So we are specifying this using PT variable here. So let's run this cell. Okay, so I did some mistake here. Okay, so it should be images. Yeah, so now we are able to run the cell successfully. So now we are just going to do our inference. We are going to feed this image and the features that we extracted in the previous step. We are going to feed both of those into the model to get the model inference for our image. And this model will be able to detect objects in the image that we provided. So in the previous task, we learned about how to prepare the inputs for the zero-shot object detection task. In this task, we learned to form the actual object detection on the provided image and add the bounding boxes and labels to the detected objects. So let's see how it works. So first, we are going to import image draw function. So we say from PIL import image draw, and then we perform the inference with this model. So we use with torch dot nograd, and then we have the outputs model. We pass in the inputs, and then we create the tensor, which specifies the target size of the image, which in our case is the size of the input image. Target size is equal to torch.tensor im dot size -1, and then we create the results variable. So we use the post process object detection function to post process the object detected results from the model. So we will pass in the outputs, the threshold, which is zero point 0.1, and the target sizes. And then we finally create a drawing object for this image using image draw function. So let's try to run this cell. Okay. So I need to pass in the target sizes here. So let's run this cell. So initially we defined our model. Okay, so now we create the drawing object for this image. Now we are going to extract the results So we are going to extract the probability scores, labels, and the bounding boxes that the model created on the image. So let's do that. So let's create a scores variable that will help us extract these scores from the results variable. So results scores to list. We'll convert the scores to a list, and then we are going to extract the labels. Results labels to list, and we are just going to convert this into a list, and then finally we are going to extract the bounding boxes from the results variable. And then we are also going to convert this into a list. That's it. And now we are just going to iterate over the detected objects and just draw the bounding boxes and the labels. So let's code that portion out. So for box, for label, in boxes, labels, scores, labels. We specify the coordinates of the bounding boxes. So it will be x min, y min, y max, x max, y max equal to box. So these are the coordinates for each bounding box that we are going to get from the model. And then we are going to use the draw.rectangle function. Draw.rectangle function that will actually draw that bounding box around around that object using these x min, y min, x max, and y max coordinates. Let's specify all the coordinates: x min, y min, x max, and y max. And then we want the color of the bounding box to be red. We want the outline to be red color. So we will specify color red here. And then we also want the width to be 1. So we specify the width as 1. And then we also, in addition to drawing the box, we also need a label corresponding to the each bounding box. So we can do this using draw.label function or draw.text function. So here we are going to say x min, y min, and we are going to specify the text of the label. So our candidate list, our list of candidate queries was in this list, text queries. So we will specify text query, and then extract the label from that list. And then we also create the score. We are going to round this scores to 2 decimal places. So we pass in the score and the decimal place. And in the end, we are just going to fill that box with white color. And here we are just going to display the image. So let's just check the function to make sure everything looks okay. So this is okay. So we have function text. So let's try to run this cell. It says that we don't have defined label. Okay. So I think this is a typo. Okay, so now it was able to detect various objects in the image that we provided to the model. So it missed out on the camera, but however, it detected the hat, it detected the book, sunglasses with their respective probability scores. And yeah, so this is the task, which is very important in real world applications because it helps you detect various objects in an image in a very straightforward way, and even for classes that the model has not seen during training. So it's a very interesting application of vision transformers. In the summary, you saw how to use visual transformer models and Hugging Face packages to perform the following task. You used image classification to get a text description of an object in an image. You saw how zero shot image classification can guess the contents of an image without you providing similar examples during training, and you used image detection to find location of objects within images. Thank you and bye bye.